everyone, I am Parth. Our group is going to implement and simulate deadlock, concurrency, and semaphores algorithms. This is our website. At first, we have given brief explanation on deadlock and concurrency. Deadlock describes a situation where two or more threads are blocked forever, waiting for each other. Concurrency means multiple computations are happening at the same time. Here is our team: Love, Parag, me, and Smith. We have added certain animations and transitions to make our website more interactive and more user friendly. From here, you can simulate the algorithms. First one is Banker's algorithm, second one is Peterson's method, third one is product consumer method, and fourth one is semaphore. Banker's algorithm is deadlock avoidance algorithm, which is used for resource allocation. It also helps the operating system to successfully share the resources between all the processes. Banker's algorithm helps us to identify whether a loan should be provided or not in the banks. Now, my friend Smith will simulate the Banker's algorithm.
I am Smith and now I will show you the demo of Banker's algorithm. First we will enter the total number of processes, then we will enter the total number of available resources. Here 10 stands for R1 resource, 5 stands for R2 resource and 7 stands for R3 resource. Now we will enter the total maximum needed resources R1, R2, R3 for every process P1 to P4. After entering the maximum needed resources for a process to get executed, we will enter the allocated resources to a process. Now for any process from P1 to P4, if a maximum needed resources minus allocated resources is less than available resources, then deadlock will not happen as a process will get executed. And after a process gets executed, the resources are free and other processes can also use that resources. Now press the submit button. Now we see the order in which a processes gets executed.
Hey guys, I'm Parag and I'll be taking over from here. Peterson's method provides a good algorithmic approach to solve the critical section problem, as it addresses the requirements of progress, mutual exclusion, and bounded waiting. Let's see how it works. We have taken two processes P1 and P2. Just as process P1 enters the critical section, the value of the turn variable changes, which sends a signal that P2 cannot enter the critical section at the same time. It is only after process P1 exits, process P2 is allowed to enter the critical section. It can hence be said that the algorithm successfully prevents deadlocks. Talking about the producers and consumers problem, it is a classic multi-process synchronization problem. Here, the producer's job is to generate data and the consumer's job is to consume data, and both of them share same memory buffer. If the producers generate data at a rate higher than the consumers can consume the data, or vice versa, then the memory buffer becomes full and the problem occurs. In such a case, semaphores prove to be useful. Here is how. First, we will add the total space in the main memory. Then we will enter the total items produced by the producer. Then we will enter the total items consumed by the consumer. Then if we press the producer, then all the 6 items will load in the main memory. Then if we press consumer, the 3 items will be consumed and only 3 will be left. Then again when we press producer, the 6 more items will be added in the main memory. Then total 9 items will be there. Then if we press consumer, 3 items will be consumed and only 6 will be left.
Hey guys, I'm Lavrai. I'll be the one taking over now. So before my fellow teammate Smith gives you the semaphores demo, let us first understand what semaphore actually is. I will just try to give you a gist of it, which won't take long. So what are semaphores? Semaphore is an integer variable which is used in an exclusive manner by various concurrent cooperative processes in order to achieve synchronization. Or we can also call it a tool which is used to prevent race condition. There are two types of semaphores. first is the counting semaphores. These are semaphores which allow an arbitrary resource count. The other is binary semaphores. These are semaphores whose value are restricted to 0 and 1. Now, Smith will continue with the demo of semaphores.
Counting semaphore demo. First we will enter the total number of processes, then we will enter the total number of semaphores. Then when we will hit the submit button, all the 6 processes will directly come to the edit state. Now we will try to push all the processes one by one. Then the first 4 will directly come to the critical section because of 4 semaphores, and the rest 2 will go into the entry state. Now when we will try to push the 2 processes in the entry state, then the access will be denied, as there are already 4 processes in the critical section. Then we will take out 2 processes to the exit state, then the remaining 2 in the entry state will come to the critical section one by one, and the process continues. Binary semaphore demo. Now first we will enter the total number of processes, then when we will enter the submit, all the 6 processes will come into the edit state. Now we push the process 1, then it will directly come into the critical section. Now we push process 2, then it will come into the entry state. Now if we try to push process 2, then it will not come into critical section, as only one process can come in the critical section. Now we will push the process 1 to the exit state, then only the process 2 can come, and this applies to all the processes likewise.